你刚才给我搞一后面几个人is then we can't do it. So it sounds like
all right. Welcome to class, everybody. Happy Wednesday. So today we will continue talking about heaps, and we will learn our first actually theoretically optimal, like theoretically as fast as you can get for sorting algorithm, which is heap sort. And we'll also learn about merge sort, which I think is a nice, intuitive sorting algorithm. Feels a lot like binary search, and that's what you will be implementing on your own, or you can work off of the book's implementation for Lab 13. So we're not going to write any code in class today, since that's what you're doing for lab, but hopefully we'll get the intuitive understanding of the algorithm, and also how do we understand how we analyze it and how we know what its runtime is. So let's hop over to review heaps. So we also talked about trees last class. So these are data structures where rather than just a list, like say our linked lists, or even arrays where we could really easily represent linear data, has just one order. Trees allow us to represent hierarchical relationships between our data. And heaps in particular are binary trees. So that means that every node has no more than 2 children. And heaps also satisfy these 2 properties. So the first one is heap order, which just says, in plain English, this just says that for any node, it has to be greater than or equal to its parents. So, for example, for this node 9 here, it satisfies the heap order property because it is greater than 5. Similar, 7, etc. So in a heap, all nodes have to satisfy the heap order property. Additionally, I mean, our root node, it has no parent, so it just satisfies that trivially. And you'll notice that what this means is that the root node is always going to be the minimum value. So we don't have a heap isn't sort of fully sorted. We might have, I think the example I gave last time was, we could have the node 8 here, and it kind of feels like that doesn't really feel fully sorted, because now I have 8 kind of feels like it should go between 9 and 7 if I was fully sorted. But it's sort of sorted, and we definitely have the minimum node as the root. So that's the heap order property. We also have the complete binary tree property, which basically just means that everything is pushed up and to the left. So we could never have in a heap or in a complete binary tree, we would never have the right child of this 6 before having its left child. So if I want to add a node to this, I have to add, there's only one place that I can add it, and it is right here. And additionally, that makes sense. It makes sense for us to call this node right here then the last node, right? Because that would have had to be the last one that was added, right, in order for us to satisfy this complete binary tree property. Yeah, any questions or comments? Yeah.
So let's say if node 5 was like cats, and then the nodes below it were like different types of cats.
Mm-hmm.
If you wanted to put another type of cat in there, would you need to reconfigure the entire tree because you can only place it on the end?
Yeah, so that is a good question, because it helps clarify. So we can use tree data structures for lots of different things. One thing we might want to use them for would be something like, a hierarchy of animal types, and so then I'd want to say, okay, under cat, I have different kinds of cats. But here, we're using a tree to store data that has what we would call a total order. So there's a way to compare every element and say this is less than this, or this is greater than this. Does that?
So it shouldn't be used for hierarchies.
Yeah, so we couldn't really, because a hierarchy, I would say, doesn't quite have that. So, you know, it's not clear, I think, if we go back to our tree slides, you know, say I have this tree. It's a really useful tree. I mean, we, as programmers, we might want to implement a tree to store data like this, but we don't have this property where it's really clear, like, is this references node, is it greater than or less than, like, this node? And maybe we could define some way, but that's not really what this data is trying to do. Instead, this data is more giving levels than talking about an order. So yeah, so our heaps are really going to be when we have data that has an order. So that could be numbers, that could be strings. We could sort strings out. We can define an order on them based on alphabetical order, length, like we do in the lab. Or we could also have data where we just have a key going along with it, and we just define, like, you know, references, comma, like this is, and we'll often call this a priority. And this is what we're going to talk about on Friday, actually. But we could say that this has key 1, and this has key, you know, bank robbery has key 5 or something like that. So we can define, but we'd have to define that order. Yeah.
So I've read on Stack Overflow that the Java virtual machine stores the information on the heap. What kind of heap is that?
Yeah, that's a really good question. So, and also in 112, so I'm teaching 112 right now. A couple people are in both. Yes, there is a part of the memory on a computer is called the heap, and it's really unfortunate. As far as I know, that memory, the name, the heap, actually doesn't have anything to do with the heap data structure, whereas the other main area of memory that we talk about a program using is the stack. And that actually is, I mean, we did a whole project on it. The stack is a stack. The heap is, I think the word heap there is just being used as like, oh, it's just a whole bunch of memory, you know. It's not order, it's not, the stack is really structured. The heap, you can access any part of the memory in the heap. So yes, that is confusing, but I'm pretty sure that my understanding is they don't have anything to do with each other.
Perfect.
But you will hear about heaps, like the data structure heap will definitely come up. It's pretty common. So yeah, where are we? We're in heaps. So yeah, at the basic level, it's nice to just think about these as numbers, but really anything that we could have where it's meaningful to have an order, we could store in a heap. Okay, what am I doing? So a really important thing about heaps is that they have their depth or their height. If you remember in class on Monday, we said that the height is of a tree. I'll call it T. If we have a tree T, like this one, we say that its height is the maximum height of any node, and the height is the number of ancestors. So for example, this node here, it has 1, 2, 3 ancestors, so we would say that this has a height of 3. And indeed, you know, what is the depth? At this level right here, the depth is 0. At this level right here, the depth is 1. This level right here, the depth is 2. This level right here, the depth is 3. So this is the max depth of any node. And so a key fact about heaps that we're going to use when we, today when we define heap sort, and then on Friday when we talk about priority queues, is that heaps have a maximum height of big O of log n. So they're roughly no bigger than log n, where n is the number of nodes in the tree. So here it says keys, but we can also just think of this as the number of nodes. And for the purpose of this class, we don't need to worry about proving this. This is kind of something that we just want to remember. But I do think that to give some intuition, it's kind of nice to just think about, well, how many nodes and how deep are complete binary trees as we just think about bigger and bigger complete binary trees. So when I say complete binary tree, I'm thinking if it has a height 1 complete binary tree is going to have a root, and then it's going to have the root has a left child and a right child. And so this has height 1, and then also if we think about what's the number of nodes here, well, it's 3. If we have a height 2 binary tree, then what is that? Well, in our height 1, we're just going to add children to each of the leaves at the bottom. So we look like this. And if we were to count up the number of nodes here, well, our last one we had 3, and we added 4 on the bottom here, so we have 7 nodes. And if we were to continue this, so for example, we can draw out just one more with my fancy copying and pasting. If I add in all of these, I could count these up. I had 7, and now I add 1, 2, 3, 4, 5, 6, 7, 8. So I have 15. And we don't have to write it out, but if I had a height of 4, can anybody tell me how many nodes I would have in that binary tree? Yeah.
31.
Yeah, 31. How did you get that?
Just double what the last player had, like the number in the, I guess the height, the previous height.
Yeah. Yeah. So the last when we had a height 3, in our bottom layer we had 8, and each of those is going to get a child, or 2 children, excuse me. So we're going to add 16, and so 15 plus 16, well, that gives us 31. And so a couple things we can notice here. So we can notice that at each level we're adding a power of 2, right? Here we added the power of 2 was 2. Here we added the power of 2 was 4. The power of 2 was 8, 16, etc. But we can also start to notice, now that we've got powers of 2 in our head, can anybody notice a pattern with the number of nodes that we're observing? How they relate to powers of 2 as a function of the height? Yeah, so they're definitely 1 less than powers of 2. So yeah, as computer scientists, we think about powers of 2 a lot. So our powers of 2 are 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, to the 5 is 32, etc. So we can always be on the lookout for numbers that are powers of 2 or numbers that look like powers of 2. And so I heard it somewhere that from the audience that what are these looking like? Well, they're looking like 1 less than these powers of 2. And so if I write height as h, so here h equals 1, h equals 2, the pattern that I would observe here is that the number of nodes, I'll call that n, is equal to 2 to the h plus 1. So notice, for example, with 7, when our height was 2, our nodes is 7, so it's 1 less than 8. So 2 to the 3 minus 1. And so intuitively, knowing that binary trees are related to powers of 2 is kind of a good intuition to have. And then, because logarithms are basically the opposite of exponentiation, the height of this binary tree is on the order of log of the number of nodes. At least this helps me with the intuitive understanding. Why do we have big O of log n as our maximum depth? Yeah, any questions or comments here? You know, on, say, the test, the quiz at the end, you'd want to be able to say, what's the maximum depth of a heap? You'd want to be able to say, oh, it's big O of log n. And also, what's the maximum depth of a binary tree, of a complete binary tree? Big O of log n.
So, why isn't why can we do big O on if you were, because I get big O for runtime, but why are we doing big O on the number of
because big O is it just relates to functions. So if I have any function, it doesn't have to be runtime. If I have any function, I can say that that function is big O of some other function. Yeah, it could be, and so, yeah, it's a useful tool. Like I could say, let's see if I can think of just a totally weird example that has nothing to do with computer science. I mean, maybe like my retirement account, over time it has compounding interest. If I knew some function that was bigger than how big than what the compounding interest is, then I could say, oh, well, my retirement account value is big O of that function. So I mean, certainly big O of 2 to the n. Like my retirement account is not doubling every year or every month or anything like that. So I can say my bank account is big O of 2 to the n. I can guarantee that throughout my life, I will not have exponentially growing cash. And that would be a true statement, you know, because my money, it takes some value every month or year, whatever time step. And if I can bound it above by some function, then it's big O of that. But yeah, thanks for asking that question, because that could definitely be confusing. Big O, it's just has to do with functions. It's not special for runtime. Okay, so let's say I have my data, it's stored in a heap, meaning we satisfy those two conditions, and I want to add something in. So if I want to add something in, we're going to take 3 steps. We will first, so we said that we identified this 7 as the last node because it's on the bottom layer, it's the farthest left. So if we need to insert a node, we know that, so this had size 1, 2, 3, 4, 5. It's had size 5, right? When we started, it had 5 nodes. It's going to have to be, after we insert, it's going to be size 6. And we know that there's going to be another node here, because that's where it has to be to maintain the complete binary tree property. But if we observe, let's say that we put a 1 in here, like we do here, we're now violating the heap order property. So we chose to maintain the complete binary tree property, but we are violating the heap order property. And so, yeah, what do we need to do? We need to restore it. So does anybody have any guesses about how we're going to do that? Or don't even tell me how we're going to do it. Where does that 1 need to end up? What special node is it going to be at the end? Yeah.
The root.
Yeah, and that's because it's the minimum value, right? So the minimum value is always going to be the root. If we'd inserted a 3 here, say, then it wouldn't be the root. But it certainly wouldn't be, we would have to move it somehow if we inserted a 3. So, okay, so we know that this 1 is going to end up with a root. Any thoughts about how are we going to get it there? Yeah.
Create a new one, put it at the top.
So we could do something like, because we have the power, these are just node objects. We can change, we could just make a new one here and sort of attach this or something like that. But then we probably are violating the complete binary tree property, right?
Well, I was saying like make another node,
Mm-hmm.
put one at the top, and then go through the rest of the nodes and like evaluate at each point and add on that newly created node.
Mm-hmm.
Yeah, so not just putting it at the top, but also like iterate over the node that we have.
Yeah.
Sounds like that still violates.
No.
We don't want to.
So you're saying, okay, I know that this one, instead of putting it at the bottom here, I know it needs to go at the top. So I'm going to put it at the top. And then maybe I'll just like walk over all the rest of the nodes and put them in. Yeah. So that would definitely work. But what would be the runtime in terms of if I have n nodes? What would be the runtime of that? What was that?
And login?
Well, what are you?
Well, it's login to go to get down to the bottom. So then it'd be multiplying that by n because we have to do that n times for every node.
Yeah. So certainly, whether or not we need to go to the bottom every time, certainly we would be touching every node.
Mm-hmm.
So it's at least big O of n. So that would mean that adding in would be big O of n. And we would really like it, I guess I didn't tell you this before, but we would really like this to be as fast as possible. And spoiler alert, we can do it in big O of log n time. So we're only going to need to touch the depth of the tree. I saw another hand.
You can just recursively compare it to its parent, and if it violates the keyboard property, then swap.
Yeah. So the technique is going to be exactly that. We can call this upheaping, or I like the term bubbling up. And so what we're going to do is, we're just going to compare, hey, 1, you're less than 6, well, swap, So 1 and 6 swapped, and now, and then after we did this, we need to check, so we swapped 6 and 1, now we need to check 1 and 2, and okay, 1 is less than 2, so it needs to go up again, and so it goes up again, and so in the end, we've only done log n comparisons because we know that all it can do is go up the tree, and we know that our height is no more than order of log n. So this is how we can add a node and then get it into the right place in a heap. Similarly, let's say we want to remove a node. Well, what we can do is, again, using this idea of let's maintain our binary tree, complete binary tree property. We're going to start off by putting it in and violating the heap order property, we're going to start off by violating the heap order property, and then we're going to restore that property. So, okay, so we want to remove the min. So in that case here, it's 2. So what do? We first take whatever our last node is, and we grab the value of 2, and we say, okay, 2 is the min. Then we take our 7, which is the last node, and we just put its value into the root. We do this in order to maintain the complete binary tree property. And then we basically just do the opposite of our bubbling up, where we say, well, 7, let's check your, are you greater than your children? Well, no, because if one of 7's children is smaller than it, then we would be violating the heap order property. So we're just going to bubble down in the same way that we bubbled up. And again, the farthest we can go is from the root all the way down to a leaf, which is big O of log n.
So, would like randomly choose to go left or right, or is it something that
I would say you would just choose one to check first, because let's say you choose to check, always check left first, then if you're greater than the thing on your left, then you just swap with the thing on your left. If you were less than the thing on your left, then you check the thing on your right. If you're greater than that, then you need to go down. If not, then you're in the right place already, because none of your children violate if somehow if this was a 4, which it couldn't really be because we couldn't have had a 4 here, but suppose a 4 did go there, then our tree would already be a heap. We would just check left, check right. Equivalently, we could check right and then left, but we're just going to say we're going to check both, whichever one. If we violate it on either side, then just go that way, whichever one we check first. Yeah, I guess one thing, maybe a sort of little understanding check for everyone to do is think about, is there only one heap? So if I give you a list of numbers, maybe they have duplicates, maybe they don't, but it doesn't require that we have duplicates. Could there be more than one heap, or is there only one heap? And when I say more than one heap, I mean, could we have choices about where we put the numbers and it still doesn't violate the heap order property? I guess I'll let everyone think about it for a minute. Yeah, did you have a question?
If you did have a 7 on the top,
Mm-hmm.
so you check the right half,
Mm-hmm.
and then you switch the 7 to 6,
Mm-hmm.
and you still violate the heap because the 6 is greater than 5.
Nope. If I have this helps answer my question I just posed. So, if I ask you on a test, for example, I could ask you, is this binary tree a heap? And so there are two things you need to check. You need to check the heap order property and the complete binary tree property. And yeah, are there any nodes here that violate the heap order property? Yeah. So yeah, maybe I need to go.
But if you are sorting and you happen to go right, you could flip it to fix one side and the other side.
Wait.
Just flip the other side.
But then you have to go and check it.
Oh, so maybe I need to check here we go. I should have thought about this before. Maybe I need to do the smaller one first and then the bigger one, rather than just either one.
So like, I guess in my head, I would think if we put the last node 7 at the top, then you grab both of its children and see which one's smaller and replace it back.
Yeah.
Is that way you know if you're smaller than two?
Yeah. Yeah, exactly. So yeah, I misspoke when I said you could just check one and then check the other. You should, because then we'd have a 6. We could end up with a 6 above a 5, but as long as you check the smaller one, and maybe this even says, okay. Yeah, so if I swap with the smaller of my children, then I should be good. And I still have the property that I only have a path of log n to follow. Okay, but for the question of can there be more than one heap for the same data, the answer is yes, there can be more than one heap. For example, this could be a 6 here and a 7 here, and I'm storing the same data, but I'm not violating the heap order property or the complete binary tree property. Okay, so we know how to add to a heap in big O of log n time. We know how to remove the minimum from a heap in big O of log n time. And so, So the big idea here is now we can actually define an algorithm called heap sort that allows us to, we start with, here it says a priority queue. We're going to talk about this on Friday, what a priority queue is, but really just a heap is what we have. So what we can do is if we have n elements, say they're n integers, and we just add them into a heap. We start with an empty heap, just add all n into the heap. Each of those operations takes log n time. Let's see. So heap sort in more detail. So let's say I start with an n element collection, however it's stored. Maybe I call it an array. I'm just going to walk over the array, and for each element, add it to a heap. So that's going to be n times something that is big O of log n. So this means that overall, big O of n log n time to add it into a heap. And then if I just do remove min n times, I'm going to get back the minimum element, the minimum element, the minimum element, the minimum element, etc. until I have, I get back a sorted array of my data. So again, I'm going to say for maybe, I'll just say n times, but we could imagine implementing this with a for loop. N times, I'm going to call, get min, which is just return the root. And we know that this is big O of log n. And so since I've gotten the min from my collection every time, I would get a list that's in ascending order. The first time I get the minimum element, second time I get the second to smallest element, third time I get the third to smallest element, etc. So again, I've got two processes that each take, I basically have 2 times n log n, which in the end gets us to big O of n log n. And so overall, heap sort sorts our elements in big O of n log n time. And so that's faster than anything we've seen in this class so far. We talked about insertion sort. We'll talk about selection sort later, which is another quadratic time sorting algorithm. But yeah. So heap sort, I think, is good to understand how we can just use this data structure where we understand, okay, it can do these things in log n time. So then we just think to ourselves, well, what can we use that for? We can actually use that to define our fastest yet sorting algorithm. Any questions or comments on that? Okay, so let's take a look at merge sort then. So merge sort is a lot like binary search. It's recursive. And the big idea behind merge sort is we're going to use a divide and conquer approach. So here, what this divide step is we're taking our input data. So say we have a list like this one. This is a list of 7, 2, 9, 4, and we want to sort this. You know, in the end, that's going to be 2, 4, 7, 9. So we have this input list, and in our divide and conquer approach, we're going to, at each step, divide that list in half. So with our 7, 2, 4, 9, that gets divided into S1 is going to be 7 and 2, and S2 is going to be 4 and 9. And then we just say, well, okay, you wanted to sort this? Well, just sort these. And then we divide them in half. So we're going to sort 7. We're going to sort 2. We're going to sort 4. We're going to sort 9. And unlike in binary search, where really we just got to do this cutting in half, cutting in half, cutting in half, we also have to have this, what is called a conquer step. So we've seen the divide step. We've said, okay, we recurse. We call it again until base case, like say when there's only one element left. We're now going to have this conquer step. And in merge sort, what that is how do we actually merge our sub-solutions back up to the top? Let's see. So I think that the best way, a good way to get some intuition here is just to see an example. So, okay, we had this, now we're going to think about this list, not just 7294, but 7294, 3861. So I want to sort 7294, 3861. Well, what do? I say I divide in half, and I divide in half. Now I'm not in my base case yet, because I'm going to say my base case is when I have only one element, because a one element list is sorted by default. So here I have a 4 element list. I'm going to recurse again. Now I've got a 2 element list. I recurse again, and now I'm finally down to a 1 element list. And so I say to myself, well, base case, okay, it's sorted, so I say return. Yeah. Yeah, that's a really good question. In that case, we just do, we can choose to either do, let's say this had 7 elements. We could either split here, we could split here. You can actually show that, it doesn't really matter too much where you split. I think maybe if you were splitting, certainly there are many split points that would work. And in fact, you could even, for simplicity of analysis, we just split into 2, but you would actually get the same overall runtime if you say split into 3 and had, rather than this binary tree of our recursive steps, we could have 3 children for each node. In the end, we would get the same analysis. And we'll actually here, you'll implement this tomorrow, but we'll also look at the code together today if we have time to see how we calculate this midpoint. This is our midpoint. Okay, so we've made it to our base case. Oops. And we say, okay, great, 7 is a sorted list. Now, we've returned, we've come back up, and so now we're going to sort our list, our 2. Okay, 2 is a sorted list. Nice. And now we're at this conquer step. This is where we need to merge these back together. So I had one function call that had this 7. It's returning 7. It's saying, cool, I got you a sorted list. This function call, it's saying, I got you another sorted list, and we're going to have to merge these together. And so we'll see the code to do this, but as these are merged back together, we merge them into a sorted list, and now we come back up to this node, and so this node now is going to sort this side. So how do we sort this side? Well, we're going to have to go all the way back down to the bottom of our recursion tree. This has skipped some steps, put them all into one slide, but we got down to our base case on each of these, and then we had this merge step, and we have a sorted list. And so now let's think about, okay, this node, this call to, say, merge sort, it's returning a sorted list. It's got 4 and 9, and this call to merge sort is returning a list 2 and 7. And so now it's a little less trivial, like, you know, maybe merging our list of 2 and our list of 7 was a little trivial to see, okay, cool, yeah, 2 is obviously less than 7, so it's going to be 2, 7. But what about when I have a sorted list? I need to merge the lists 2, 7, and 4, 9. Anybody have any thoughts about how do I create a sorted list out of these 2 lists that I am guaranteed that they're sorted?
And they're only 2 long?
No, maybe in general we say, we'll skip some more steps. We'll get back to, okay, now let's say I have this one, and I need to merge them. I want to have one function that's just going to be able to merge sorted lists back together. And I'd like to do it fast. I don't want to have to I don't want it to take quadratic time. I don't want to compare everyone to everyone. I want to just walk over each list once. Yeah?
What if we just chuck it in a heap?
Ooh, that is a good idea. That would definitely work. And it wouldn't be quadratic, so that's really good. It would be n log n. But we can do better. We can actually do it in just the length of the combined lists. So here the combined lists are 8. So we essentially only need to only need to look at each one once, essentially. Yeah.
So because they're sorted, you can just compare corresponding indices, I guess.
Mm-hmm.
Arrange each pair properly, and you should get line up all the way through, shouldn't you?
Yeah, I guess the way I think about it is, if I have 2 indices in these lists, and I'm going to only move one index over when, let's see. So here I see, okay, on this side it's a 1, so I'm going to put a 1 in. And then I look at my next one over here, so I'm going to move this index over. But now 3 is less than 2, so I'm going to take my 2 from over here, and then I'll move this index over. But now, okay, maybe I stay with this list, but I check against my other index, pointing at the 3, and it says, well, okay, my 4 is greater than my 3, so I'm going to take this 3. Now I'm pointing at a 6, but 6 is less than 4, so I'm going to take the 4. Now I've moved to 7, but 7 is greater than 6, so I'm going to take the 6. This one, very much we're just crossing over every time, but you could imagine that sometimes you're going to take a run from one before moving on to the other one. But in doing these, having these 2 pointers that just are going to move along, we only essentially need to touch each spot once. We're not having to compare, 2 to 1 and 2 to 3 and 2 to 6 and 2 to 8. Or even having to put everything into a heap. So that's what when we say the merge step of merge sort, we're talking about how do we merge our 2 sorted lists together into one. And so I think okay, let's look at our so our overall, if we were to give pseudocode, meaning not actual code that we could type into Java, but just a summary of the algorithm, for merge sort, what do? We just divide our list in half. We create S1 and S2. We call merge sort on each side, and then we do this merge step. Oops. And so when we implement this in Java, it makes a lot of sense to actually just write a method to merge 2 sorted lists. Since you're going to be doing this in your lab, I won't go into the details here, but you can look at this in the lab. And then if we look at the actual Java code, we're actually running this merge here. Otherwise, just doing what that pseudocode said, make our 2 copies, call merge sort on them. And since we don't have that much time left, I will keep our analysis of merge sort until next week. But if you want to think about it, spoiler alert, it's going to be big O then log n. So you can think about how we get that analysis. It's a tiny bit more complicated. We have to do a little bit harder thinking than for binary search. Remember, binary search was log n, but for this we're going to, and our big idea when we analyze recursive algorithms is we say how many recursive calls and what is the runtime of each recursive call. Here, each recursive call, it's different sizes, right? My recursive call here is really small. My recursive call here, my data is bigger. And so you're going to have to think about how do we deal with the fact that my data size is different at my different levels of recursion. But in the end, we get n log n, so that can be a hint. All right, have a good rest of your day, and see you Friday. Oh, I need to...